Hey everyone, so we're going to talk about the next part, which is vertical projectile motion. The next few videos that we watch will end up being essentially the projectile aspect, objects being thrown in the air, and how to deal with them. Now, this is by far the easiest of them because there's really not much of a difference between what we've been doing and this stuff. The only difference is there's a little bit more of hidden information now or implied information when they give a problem. In particular, you just need to be aware of what information you know going into the problem once you realize that it's a vertical projectile problem. So, free fall problems, what we mean by this is essentially that they are objects that are only being affected by gravity. They're moving in the air without any sort of contact with anything. There's no parachutes, there's no engines, nothing like that. The only thing affecting it is gravity. Now, of course, this is the ideal scenario because technically, freefall objects that are experiencing freefall can also experience another type of force, which is called air friction, which we'll get to later on. But for the most part, we're going to say that the only thing affecting its motion is acceleration. Now, we found out what the rate of acceleration is for objects that are in the air. It is 9.8 meters per second squared down. This number is on the reference table, but honestly, we use this number so often that you're not gonna have to memorize it. You'll just know it. You will never have to look at it on the reference table. The only issue is making sure that you don't accidentally think that the acceleration is 9.8 when it isn't. This is only the acceleration for objects that are in the air. If you're not in the air, if you're not falling in the air, you're not flying through the air free of an engine, your acceleration it won't be 9.8. So 9.8 is only when you're in the air. If you're on the ground, not. We use the symbol G, to represent this because it's the acceleration of gravity. Though this also does have another name. This is also called the gravitational field strength, but you're probably, at least for now, only going to see it as the acceleration due to gravity. Another thing to point out is the number is 9.8, but for the most part, you can always round this number to 10. In fact, the AP tends to round the number to 10. Why am I telling you 9.8? Because there are some questions where when you use 9.8, you'll get a closer number to the answer because sometimes with the rounding and everything, don't overthink it too much. My opinion is just use 10 and then pick the number that's closest. You'll never get the answer wrong if you use 10 instead of 9.8. That tends to be a common thing that people ask. Another thing to keep in mind is that the 9.8, that's the value of the acceleration, and the direction is always down. This is an acceleration, which is a vector. So that means that when we go to plug in this number into an equation, we have to make sure that we put the appropriate sign. Uh, when we do these problems, for the most part, I think I'm going to want to try and keep to the convention that up is positive and down is negative, just so that the future projectiles that we end up doing end up making more sense and we end up getting problems that are more consistent. Like I said, it'll make more sense as we continue on. Now, this is a typical free fall problem. We have an object that is dropped from some height, and they want us to figure out how much time it takes for the ball to hit the ground, and they want us to figure out what the velocity is. Now, at first, you might look at this and say there's not enough information, and that's true. There's not really enough given information, straight up. They really only tell us one number. How are we supposed to answer when we need, for the most part, at least three more pieces of information? And the answer is a lot of this information is actually hidden in the problem. Like, for example, uh, when they say that the object is falling in the air, we know what the acceleration is. It's 9.8 or 10 meters per second squared. So just knowing that it's in the air falling, we already know what the acceleration is. But we also have another piece of information, which is the initial velocity. They said that the object was dropped, which means that the initial velocity is zero. Now, that doesn't mean all free fall problems will have the initial velocity zero. There are times where we might end up throwing the ball. We could either throw it down, in which case the initial velocity will be negative, whatever they tell us, or it could be thrown upwards. But in this case, when you see the object is dropped or released or let go or any sort of implication that the object isn't being thrown and just kind of starting at zero and then beginning, we know that the initial velocity is zero. Um, and Yeah, so this is kind of what I was saying before. I think for the most part, I'm gonna try to stick with the up is positive, down is negative. But you might find every now and then that I just kind of say if everything is going down, I might just say that down is positive just to make life easy. But it's really up to you. All right, so here's the first video. Pause the video, work itself. I'll go in a second. All right. So let's actually answer that problem. We have a ball dropped from a height of 5 meters, and we want to calculate the length of time it's in the air and the velocity it hits the ground with. So first, to find the time in the air, well, let's write down all the given information. So it starts at some initial height of 5 meters. When it hits the ground, we're going to say that that final position is 0 meters. Because it's dropped, the initial velocity is going to be 0. I don't know what the final velocity is. I know the acceleration is -10, again, because of the fact that acceleration is always down. And then time, I don't really know. So based off the information, if I want to find time, the only one that kind of makes sense is to use the knowing x. Now, of course, I could answer this out of order. That's perfectly fine. If you want to do velocity first, do that. But if we do the annoying x equation and plug all the numbers in, we get that the time it takes to hit the ground is going to be 1 second. Now, I want to clarify this with the velocity hits the ground. Do not mistake this with the easy answer of saying it's 0. Yes, I know that when objects fall and hit the ground, they come to a stop, but that's not what they're referring to. They're referring to like the velocity it's hitting the ground with, in the sense with if you were underneath it, what would it hit you with? If you put your hand at that location, what would it, how hard would it hit down on your hand? You wouldn't say, oh, it just hits at 0 because, that wouldn't make any sense. So we're talking about the final speed just before it hits the ground. Um, so here we really could have used either timeless or the acceleration equation. I'm going to go with this one only because it's the easiest one to work with. So we plug the numbers in and we end up getting that the final velocity is -10 meters per second, which makes sense because it is going downward, right? It's when it hits the ground, it's moving downward, so the velocity should be negative. All right, here's the next one. Pause the video, work yourself. We'll go in a second. All right. So this is basically the same question, but now it's being thrown downward with an initial speed. So for the most part, the starting information is all the same. The only difference is that the initial velocity is now going to be -9 to represent that it's going down. Uh, we're pretty much going to do the same thing. But this time, actually, I'm not going to do the annoying x to find it because the equation when we work with it will end up being a little annoying to solve for time first. So instead, I'm actually going to solve for the final velocity first. So I'm going to plug the numbers in, and I get the answer is -13.5. Now, here is the key thing, and this is actually one of the reasons why I tend to try to avoid using this equation, except for some special cases where I'll just say now, if you try to use the annoying x equation, you end up with a quadratic because you have the v naught with t, and then you have the t squared with a, and you also have an initial position. So, you have to do the quadratic equation. So that's why I want to avoid it. But here I do actually have a very similar situation. uh, the thing to keep in mind is that because this is v squared, when you take the square root of both sides, that you have to check, are you doing positive or negative? Because the square root of 1 is both 1 and -1. So that's what happened here. Technically, when you do the square root, you get 13.5, but we have to evaluate it before we say that's our answer because there might be a negative on that number. So we have to say, okay, well, what direction would the velocity be? Okay, it's down, so we have to put a negative in there because there's no other way. The equation doesn't naturally give us the negative in it. So for time, we're going to use the acceleration equation. So Vf equals V naught plus AT, and we get 0.45 seconds. All right, here's the next one. Pause the video, work itself. I'm going to go in a second. All right, so here we're going to sketch the three graphs. So we have our position, our velocity, and our acceleration graph. And we're going to assume that the ground is going to be 0. Now, personally, I always like to work backwards on here. It's just a lot easier because for the most part, like I said, acceleration in this class is going to be constant, which means I only have three options. Is it 0? Is it positive? Or is it negative? Those are the only three options. So in this case, what we're going to say is the acceleration is a constant -10. So we're going to start off with I guess here I went backwards, but I'll mark up instead. So the acceleration would end up being negative, constant. Then what I would say is to the velocity. Now, what I would say is to kind of almost like plan out and plot certain points. Because this graph is constant, we know this graph must be a linear graph. So I know I'm making a line. The question is the line going up? Is it going down? Is it starting positive at 0 or negative? So I'm going to start with that one. Where is the line starting? If the object is in free fall, they didn't say whether it was thrown up or thrown down. So I'm going to assume that it is starting off at 0. Now it's starting being dropped. And now looking at this graph, because this graph is negative, that means that the slope should be negative. So my graph should go down. So here's my linear line starting at 0, going down in the negative. See how I set that up? I started off talking about where my starting point is, and then I kind of worked my way backwards. Here, I'm going to do the same thing. I know that my position starts off in a positive direction because I'm starting off up in the air. I know eventually I'm going to go down to 0. Because this graph is linear, that means that my slope here is going to be changing. So this means it's going to be curved. Now I have two options. Is it going to be curved this way or is it going to be curved this way? Um, because this graph starts off at 0, the slope of this graph has to start off at 0. Always relate what the graph is doing on the previous one to what the slope is doing on the one you're looking at. So this graph starts at 0, so my slope should start at 0. So it should start off flat, and then as time goes on, it should become steeper and steeper. So my slope ends up or my graph should end up looking like this, with a slope that is constantly increasing in the negative direction. So this is what my three graphs would look like. And notice how I did that. I worked backwards this way. I started off with my acceleration, recognizing that it's negative and then constant, and then finding the initial point of my velocity before coming with the realization of the linear part, all that stuff. This is probably the hardest thing for a lot of people is being able to sketch graphs of what things look like. And my go-to is always to say, to try to identify certain points. Try to identify what the initial point is, what the final point is, and where any zeros are. And then worry about how those points are connected. Are they connected with a line or a curve? But if you kind of just do that and note where certain starting and final points are and 0 points are, a lot of times you might find that you end up getting majority of the points even if you kind of connect the points incorrectly. All right. So we're gonna move on to just gonna turn off the pen. All right, so we'll leave it there. In class, we're going to talk about what happens when we have objects falling and experiencing air friction. So far, we've been talking about the ideal case where there is no air friction. We're going to talk about it in class, what happens when there's air friction, and keep in mind that it's going to be just a conceptual thing. All right, you won't ever have to do any math problems with air friction. All right, if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.